Hi, this is Rick Colt. Today we're going to develop a VisSim embedded application to blink the red LED on the Texas Instrument F28069M LaunchPad development kit target using a frequency command sent from a VisSim slider block. The application will also measure the LED on time and communicate that value back to the host in real time, where it will be displayed in plot and display box. This example illustrates host to and from target communications using interactive data exchange. All communication is done in real time. A slider block on the host will send a frequency command to a square wave signal generator. The 50% duty cycle square wave will blink the red LED on the target at the frequency specified by the slider. Additional logic on the target will be developed to measure the on time of the square wave during each of its cycles. That value will be returned to the host, where it will be displayed in plot and display blocks. The models we're using in this diagram are listed below for the source and the debug. In step 1, we will create and simulate the source model. To start with, we need an F28X config block located under Embedded, Piccolo, and at the top of the list, the F28X config, configured correctly for the CPU we're using. Next, we will place a slider located from Blocks, Signal Producer, slider, and attach it to a variable that we'll call frequency Hertz. We will configure the slider to range from a lower bound of 0.25 to an upper bound of 5 in increments of 1. From Diagrams My Models, we will select and place our repeating time model on the screen and we'll attach the frequency signal to the input of the repeating time block. We will create the square wave by taking the input to the cross detect block and comparing it with 0.5 and labeling the output as square wave. This output will range from 0 to 1. To measure the on time of the square wave, we will place a cross detect block on the screen and connect it to the square wave, setting the cross point to 0.5. The cross detect block will then output a +1 pulse when the square wave transitions from 0 to 1, and a -1 pulse when it transitions from 1 to 0. We are only interested in the 0 to 1 transition, that is the on to off transition, so we will pass the cross detect through a limit set to 0, 1, and in turn use that pulse output to sample the output repeating time signal and capture it in the variable on time. To test the source model, we will simulate it at 4 frequencies, beginning at 0.25 Hz, and observe the square wave and the on time. As I start the simulation at 0.25 Hz, we see the square wave with a period of 4 seconds, on time of 2 seconds. As I move the blink frequency to 1.25, I see the on time move to 0.4 and the period to 0.8. Similarly, when I move to 2.25, I see a period of 0.44 seconds with an on time of 0.22. And finally, moving to 5 seconds, I see a period of 0.2 and an on time of 0.1. With the source model now operating correctly, we will create code. To do that, we need to encapsulate the algorithm into a compound block, and I'll call it target calculations. With the compound block created, we'll simply lasso it, go to Tools, Code Gen, make sure the Include VisSim Communication interface is selected, taking the remainder as defaults, compile, press any key to continue, and quit. At this point, we have created C code for the source model. We will now rename the source model as the debug model by appending a -d to its name. We will edit the debug model by first replacing the target calculation block with an embedded Piccolo target interface block and configuring it to access the .out file previously created. We will set the system properties to a millisecond update with an end time of 50 seconds running in real time and begin our simulation. Now, as I begin the simulation, you'll see the red LED blinking on the target board at 1/4 Hz. As I increase the frequency, you will see that LED increase in frequency. I'm also recording the on time in the plot box, showing the data that's being passed from the target back to the VisSim host. As I increase to 2¼ Hz, again we see the red LED blinking and our on time decreasing as expected. And moving up to 5 Hz, we see our on time decrease to 0.1 and see the LED blinking at 5 Hz.